to ask this again. Does anybody mind that I'm videotaping this and then I'm going to put it online for you after, just in case if you missed anything, or if you can't come to one of the classes, you can't make it for whatever reason. You can see it online after, but please still come to class. That's not an excuse not to come. So welcome to 664. My name is Samir Adib. I will be teaching you the first half of the class. And for the geotechnical students, Dr. Dave Chan will be teaching you the second half. The structures students, they will continue with me. The geotechnical students will continue with Dr. Chan. Dr. Chan also informed me that the geotechnical students, they have to be in a certain lab next Wednesday. He sent me the email that I didn't printed, but do you guys know who's in geotechnical students here? Do you guys know what lab you have to be in next Wednesday? Who doesn't know? Oh, okay, well, we do have time to check that out. This announcement. You need to be in the next Wednesday, September 12th at 2 p.m. in room L1-120. Okay? In case you were wondering, you have a certain schedule for the lab. For 60 geotechnical students. 60. That's what it says. Okay. Any questions about this? Which I probably wouldn't know how to answer. All right. So the mark distribution for the course will be 20% for assignments, 40% for the first midterm, 40% for the final exam. For the textbook, there is a textbook for your course. If you've taken 398, if you already bought that textbook last year, you can use that textbook from last year. If you haven't bought it, if you don't have it, the text this year is available as an e-book through the Civil Engineering Club. You can buy it online from the publisher, but then the publisher makes all the money. If you buy it from the Civil Engineering Club, you're supporting the Civil Engineering Club. The reason why I'm going e-book, because I'm not really making any money out of it, it's the publisher, so I'm trying to save, so they're saving about $40 to make it an e-book rather than a full book. There will also, for the second half, there will also be class notes provided by myself and by Dr. Chan. Throughout the course, you need to know how to use the software Mathematica. There's a lot of calculations in the book, throughout, there are a lot of calculations in this course. Now, I do not focus on how to calculate the eigenvalues and how to calculate the eigenvectors. I don't really, if you know it once, that's fine. I don't really question whether you know how to calculate it or not. What I question is, do you actually know what you're calculating or not. That's very important for me. My question is, do you know what you're doing, not how you do it? And that's why I'm asking you to use the software Mathematica, because Mathematica allows you, it just does the calculations for you. Of course, you can use whatever software you want, but the textbook already has most of the code you need to input into your Mathematica software. So, how to get the software? You have three options, and I'm going to talk about this in a second. The course outline, first we're going to talk about introductory linear algebra. I'm going to cover linear algebra for the first 2 to 3 lectures. And if you've taken 398, it's going to be, you've already listened to most of what I'm going to be talking about today. Perhaps the difference is that I focus now on the proofs rather than just presenting the final results. Then I'm going to talk about the stress, what the stress means, and what the word strain means, and then we're going to talk about constitutive equations for linear elasticity and formulation of elasticity boundary value problems. And then right here, the structural engineering students and the geotechnical engineering students will split, and then other topics will be covered. Now I cover a lot of, I realized that I cover a lot of things in this course, and I expect it goes really fast, because it's almost every week you have a brand new topic. It's 3 hours, and that's why I'm trying to make it easier for you. If you miss something, or by the end of the 3 hours you're kind of falling asleep, you can find everything online. So this is the tentative schedule. You have all the different weeks. September 19th, there will be no lecture. And on October 24th, you are going to, that's when we start splitting. The geotechnical students will start with Dr. Chan. The midterm will happen sometime at that time, or during that week. It's tentatively scheduled for Saturday, October 27th at 9 a.m. for 3 hours. So if you have any comments or any questions or any suggestions, please email me. You have some references list. If you really enjoyed this material and you want to read more about it, some of these references are a little bit outdated, but if you're very interested and you want more, you want to read more about this, do not just email me or ask me, and I can show you a nice book about this topic. So before I start, I just want to show you a few things about course management. So if you go to E-class, and I think you see the same thing as I see here. On E-class, you're going to find everything, hopefully everything that I say. So the first thing you're going to find is the course outline, the available options using the Mathematica software. There are 3 options for you to use the Mathematica software. The first option is for free, using the virtual computing laboratory, available for CV 398 students and for the graduate students. You have to use your CCID and password, and you can view the instructional videos here. You can buy a student license for $45 directly from Mathematica and have it on your own computer, or you can contact AICT and see how you can install it on your computer if it's possible. But if you But if you want to access it using the virtual computer laboratory, which basically you need to remote desktop connect to another computer that has Mathematica, follow the instructional video, which you're going to have here. It says here how to connect to the virtual computer lab, and these are videos that I posted online for CV398, and they also have some lectures for CV398, which is basically the prerequisite for this current course. So these are your available options. The online Mathematica tutorials, if you're not following what I'm saying, or if you're not following what the book is saying, you can follow the online Mathematica tutorials and the undergraduate course lectures. You find here Introduction to Mathematica for Solid Mechanics. If you click here, you're going to have a bunch of videos that you can look at. All the assignments are already posted. If you really enjoy the material and you're just going fast, you can do all the assignments already. So the first half, you've got 6 assignments. The combined group length lectures. So usually what I like to do, so I post the lecture online. So you have all this material. It's already online, and you also have the lecture with just the titles, and you can write during the lecture if you want. If you print this at home, and then you come and you can write here what I talk about during class, or you don't even have to take notes, because whatever I write, I will be posting online afterwards. So you have the first 5 lectures are already posted if you want to print them, or even if you want to take a look. Alright, so this is it for you missed the most important part. Do you guys have any questions? Yes.
I just checked the class isn't there yet, so I'm just gonna.
E-class?
Yeah, it's not E-class yet.
Maybe there's something I have to do. Okay, if you can't access it, if you can't, I don't want 30 emails saying I can't access it. So I guess that's fine. I'll note to self. All right. So let's start. What is solid mechanics? So solid mechanics is the study of stresses within solids. We're trying to predict the deformation of solid objects. We're trying to study the failure criteria of objects. And we want to use the Newton's equations of motion to predict the behavior of models, or the behavior of objects. So a lot of people ask, well, how am I going to use this for? You're going to use this for programming Angry Birds. Whatever, if you've seen Angry Birds, That's exactly what they do. First, you put some strain energy inside an object. This strain energy is transformed into some kinetic energy. This kinetic energy is used to, I don't know, it just transformed to kinetic energy of the angry bird. The angry bird hits an object. Depending on the stresses within the object, depending on all these things, you decide whether this object has failed or not. Basically, solid mechanics is exactly this, but instead of making it fun and studying angry birds, we're going to study the buckling of objects, the deformation of objects. And so at the end of the day, I don't promise you that you will be able to produce those color pictures. Those color pictures are produced by finite element analysis models. But what I would promise is that you would understand the meaning of the color pictures that you see. All right. So, what we are talking about is, the topic is called solid mechanics or continuum mechanics. And the first thing that I would like to cover is, how can I represent a continuum, or how can I present something that's continuous? Because all the objects, everything that we do here, we assume that things are continuous. And our ability to present continuous objects stems in our definition of the real real numbers. Now, a real number, and I'm quoting Wikipedia, a real number is a value that represents quantity along a continuum. And this is not a rigorous definition, but you probably should, if you're interested, perhaps read the Wikipedia article about real numbers. But basically what real numbers allow us to do is the following. We can only count. So I can count a point here and a point here. The ability of what real numbers allow us to do is to say between any 2 points I can find another point. And between those 2 points I can find another point, and so on and so forth. So the real number allows us to describe something that's continuous. If we only look at the rational numbers, we're not able to define something that's continuous. We need what we call the real numbers. Now, whatever the properties of real numbers, they translate into properties of any continuum, or any object that lies in space. So I'm going to look at the properties of real numbers, because I'm going to use these properties when I define linear vector spaces. And the first property is that the real set of real numbers is closed under addition. What does this mean? It means if you have any 2 real numbers, you add them together, you're not getting out of the box. You're still inside the box of real numbers. It's closed under addition. Whatever, any 2 things that you add, any 2 real numbers you add to each other, you're going to still end up with the real number. And that's what we mean by closed. The set of real numbers has a 0 element. What does it mean that it has a 0 element? There is. If you add 2 plus 0, you end up with 2. This is one of the properties of the real numbers. It has this 0 element, which is neutral in addition. Also, every element in R has an inverse element of addition. If you add 2 plus another number that we call -2, you get 0. Now, what is -2? I mean, -2 is just the opposite of 2, which is basically the inverse element of 2. R is also closed under multiplication. If you multiply 2 by any real number, root pi, you're going to end up with 2 root pi, which is also still a real number. Whatever two numbers you multiply by each other, you'll never get outside the box. Now throughout the course, we're going to be using some new symbols. These new symbols are designed just so that the text, the stuff that we're writing, just to reduce the number of words that we put on the page. And it's basically, for some of you, will be a new language. Once you master it, things will be very easy. So, R is the set of real numbers. Any real number belongs to the set of real numbers. Belongs to R. N is the set of natural numbers. Natural numbers are starting from 1. Is the set 1, 2, 3, which is basically the set of counting numbers. Whenever I define a set, the set is defined using the curly brackets. So A, this is a set of elements. So the elements are 1, 2, and 3. An element belongs to a set. This symbol indicates forever. So I can say I have A is equal to 1, 2, 3 for every element in A. This element is greater than 0. There exists, if I say the set B is equal to 1, 2, 3, negative 1, negative 2, I can say there exists an element in B, and this element is less than 0. There exists and unique. I can say that B is equal to 1, 2. Let's just use a different symbol. C and negative 1. There exists an element in C, unique, such that C is less than 0. There's only one of its kind. So when I see this exclamation mark, it implies that this element is unique. If you look at the sets above, if I relate sets to each other, if I want to know which set lies inside which set, I can see that the element 1, 2, and 3 are also elements of B. I can say that A is a subset of B. The next symbol that I use is when you define a function from a set to a set, I use this arrow. So if I say I have a set A has a few elements, and set B has other elements, I can define a function from A to B. This function is defined or written as follows. F is defined as a map from the set A to the set B. Example, f of x equal to x squared. F is defined from R to, for example, this open set of real numbers. You could give me any, f maps any real number to a number between 0 and infinity. there's another arrow. When I use this arrow, I'm putting two sets on the side of this arrow. I can also say for every element in A, F gives me an element in B. And then I use this different arrow. If I'm using an element here and to an element here, then I use this arrow. A cross B gives me the set of ordered pairs made out of elements of A and B. So let's say A is equal to 1 and 2. B is equal to red and green. The set A, B is equal to the set made out of ordered pairs. 1 red, 2 green, 1 green, 2 red. This is A cross B. Sometimes, if I use ST, I mean, it means such that. This is an example of everything that we talked about for, right now. What we're saying here, this operation, the addition operation, is defined on the set of ordered pairs of x cross x and gives me a result that's also x. So for example, I can say that the addition operation is defined on any two real numbers. Give me any two real numbers. I do a certain operation. This operation is addition, and the result.
I'm sorry, we went to the wrong upstairs.
This one. I should know better because that happens every year. Geotechnical students, you have for those who just arrived, who are geotechnical students, you have a lab next Wednesday. So ask your other geotechnical students what kind of lab you have next Wednesday and what room at 2 o'clock. Okay, so the next thing that we need to cover in the symbols that we're using are those 3 symbols. One means equivalence. This arrow means one statement leads to the other. And this symbol allows me to define sets using properties. So let's see the difference. Let's say A is a subset of R. This leads me to the fact that for every element in A, this element has to belong to R as well. I can also say, if I start from this side, that for every element in A, this element is an element of R as well, that leads me to the other side, which means that A is a subset of R. Since starting from the left leads to the right statement, starting from the right statement leads to the left statement, that means that the two statements are equivalent. F, or that's A is equal to 4. This leads me to A is a real number. But A is a real number does not mean that A is equal to 4. So these are not equivalent statements. So you have to differentiate between equivalent statements and statements that lead to other statements. In order for me to define sets, I define sets as follows. I can define a set using a property. I can say the set A is equal to all the possible x's such that those x's are between 0 and 1. And this is not enough because I have to tell you what x could be. Because x, if x is only a natural number, then the only thing that A can have is 0 and 1. I have to tell you what x is. So x is a real number. So those properties tell me what A is. So A is equal to the interval 0, 1. If I tell you A is equal to all the possible y's, where y's are between y, 0 and 1, and the y's are only natural numbers, then this is equal to the set of the two numbers. We said that natural numbers, let's just put 1, 2. So these are just the set A contains only two elements that are 1 and 2. So we're going to use all those symbols to talk about linear vector spaces. Why would we like to talk about linear vector spaces? We need to talk about linear vector spaces because all our objects, anything that we're going to analyze, being solid, being soil, being even fluids, anything that we're going to describe, we're going to put this object inside a three-dimensional vector space. Because we're going to put this in a three-dimensional vector space, I need to understand the properties of the vector space in which I'm putting my objects in. So, let's see what all the following sets have in common. R squared, by R squared I mean R cross R. The set of ordered pairs that has two numbers. R3 is the set that has three numbers. Each element is three numbers. R power n is R cross R n times. M3 is the set of all matrices that are 3 by 3. Mn is the set of all matrices that are n by n. Square matrices. That are n by n. And the one that doesn't look like the rest of them but has the same properties is V is a set of f, where f is the function defined from 0 on the interval 0, 1 to r. What are the elements of V? The elements of V look like this. I have from 0 to 1 this interval. V is equal to any function that's defined on this. So f1, this is an element of V. f2, this is an element of V. f3, again, this is an element of V. So what do all these things have in common? What they have in common is that if you have 2 and you add them to each other, you're still lying in the same box. If you have 2 elements in R2 and you add them together, you're still lying in the same box. If you have 2 matrices and you add them together, you get another matrix, still in the same box. If you have 2 functions defined on the interval from 0 to 1, you add them together, you get a third function that's also in the same box, that's also lies in the same set. So they all have, what they all have in common so far is that if you add 2 of them, 2 of the elements of those sets, you end up in the same set. Each of those sets as well, each one of them, every element has a 0 element. So there is a 0 matrix that's 3 by 3. 0, 0, 0, 0, 0, 0, 0, 0, 0. There is a 0 vector that has n entries. There is a 0 function. The function 0 defined on the interval from 0 to 1. So all of these sets have a 0 element. And all these sets have an inverse element of addition. For every f, you have another one, negative f1, which when you add together, you get the 0 element. For every vector in Rn, for every x in Rn, there exists negative x, such that x plus this negative x equal to the 0 vector. So all these sets share the properties of the real numbers or inherit the properties of the real numbers. And that's why we define these sets in an abstract way as follows. This definition applies to all the sets and many more that we talked about. So a linear vector space, all of the above sets